Hello everyone. Today we will be doing a physics problem submitted by Fahad Hamdan. Fahad, if you're watching this, salam alaikum. A bullet with mass m hits a ballistic pendulum with length L and mass m and lodges in it, big M. When the bullet hits the pendulum, it swings from the equilibrium position and reaches an angle alpha at its maximum. Determine the bullet's velocity. So if I were to approach this problem, I would split it up into two phases. Phase 1 and Phase 2. In Phase 1, we have a pendulum at rest with an object hanging from it with mass big M. And we have a bullet traveling at velocity vb, this is the velocity that we're trying to solve for, with a mass little m. Now, I know that the bullet and the object are going to collide. Whenever we have a two-body collision, we think about the conservation of momentum. So if I look at the total momentum in this system before, it's going to be the mass of the little bullet times the velocity of the bullet plus, there's going to be no momentum with the object, so that's just going to be 0, is equal to, now when the bullet collides with this object, it lodges in it, meaning that the bullet and the object are going to travel at the same speed, vf, same velocity, sorry, and the new mass is going to be the mass of the object, big M, plus the mass of the bullet, little m. So if we solve for the velocity of the bullet, we get the velocity of the bullet is equal to the final velocity of the combined object plus its combined mass all over little m, the mass of the bullet. So now we have an expression for the velocity of the bullet. So we know the mass of, well, we have the mass of m, and we have the mass of big M. What we need to find is the final velocity of the combined object. So that's where phase 2 comes in. If we consider this to be the vertical, we know that after the bullet collides with the object on the pendulum's going to swing upwards. So this is where it's going to be with mass big M plus little m. It's going to make a angle alpha, and for the sake of my sanity, I'm going to change this angle alpha to angle phi, because every time I try to write an alpha, I get a stroke. Angle phi. So when we're looking at this phase 2, we know that the final velocity of, at the end of phase 1, the final velocity of phase 1 is going to be the initial velocity of this object at the beginning of phase 2. Now, how do we find the initial velocity at phase 2? We know that it is at its maximum. When it's at its maximum, an object on a pendulum, the total velocity is 0. So you could try, you know that this is moving upwards, so it has some horizontal displacement x, it has some vertical displacement y. You could try analyzing it that way. If you try to consider it a projectile, that would be wrong, because if you draw a free body diagram, there's the force of gravity acting on it, and there's also this tensile force coming from the string of the pendulum. So analyzing it in a projectile motion framework will not work. I'm sure there is a way to figure it out this way, but I don't have the time nor the energy. So, speaking of energy, how we're going to approach this problem is using the conservation of energy. We know that in phase 1, it is at a height 0. We're going to say that is h equals 0. This is where it was before. Now, it's swung upwards, so it gained some height h. When an object is gaining height h in a field of gravity, we can apply the conservation of energy. So at the beginning of phase 2, which is basically the end of phase 1, we know that the kinetic energy 1/2 mv squared. The kinetic energy, we know it's going to have some kinetic energy because of the bullet that just imparted an impulse onto the object. It's going to have some kinetic energy. So it'll have kinetic energy with a velocity v, and this velocity v just so happens to be this vf that we have in the first expression. Because the kinetic energy, the only way it's going to have kinetic energy is if it has a velocity. And that velocity is the same velocity that it obtained after it collided with the bullet. So we can say that this is mvf squared, where these two are equal. And it's going to have zero potential energy because we just defined the bottom to be h equals 0. So we set that equal to, now, what is the final energy? When it's right here, it's at its maximum. When a pendulum is at its maximum, it has 0 velocity, so we know it's going to have 0 kinetic energy. However, it gained a height h, so against a field of gravity. So we know it's going to have some potential energy, which we can say is mgh. Solving for vf, we get vf is equal to 2gh, all square rooted. Now, we have an expression for vf, which is what we needed in this first one. So we can rewrite this as v is equal to root 2gh, big M plus little m, all over little m. Okay, so again, we know both the masses. In theory, that's what they've given us. But what is the height h? Now, if we go back to phase 2, we're told that it makes an angle phi with the vertical. So how can we use that to our advantage? We know that at the beginning, the distance from the top, the roof, where the pendulum is attached, to the object is L. The distance from the roof to the object will simply be the length of the string, L. Let me rewrite that right here like this. It's going to be the length of the string. However, when it swings, it's gained some height. So the distance between the roof where it's attached and the object will no longer be the length of the string. It will be, so if we say this is the roof, it will be the length of the string minus whatever height was gained, L minus h. And we know that the length of the string here is not going to change. It's still going to be height L. So how can we find h? Well, we can use our good old trigonometric functions. We know that this angle right here is 90 degrees, or pi over 2 minus phi. So we can say that, scroll down here, the sine of pi over 2 minus phi is equal to y, L minus h, all over the hypotenuse L. Solving for h, we get h is equal to L minus L sine pi over 2 minus phi. Now, sine pi over 2 minus phi, that is a cofunction identity, so we can rewrite that as h is equal to L minus L cosine phi. If you wanted to, you could leave it like that, but it doesn't look good and it can be simplified, so you might as well. This is L, and then you can further simplify by factoring out L, say 1 minus cosine phi. Now, we plug that back into the expression we got before, and we get that the velocity of the bullet is equal to root 2g. Now we know what h is. L times 1 minus cosine phi times big M plus little m all over little m. And that will be your solution.